Let's talk about L'Hopital's rule. This is a new method of computing limits, an application of the derivative. Check it out. In order to motivate L'Hopital's rule, let's start by looking at an example. So we'll look at the limit as x approaches 1 of x minus 1 divided by the square root of x minus 1. Now we've seen this kind of limit before. At the beginning of the term, we would have computed this limit by taking that function there, the fraction, and multiplying by the conjugate of that term in the denominator. So we would have taken the conjugate, meaning that you change the minus to a plus, and then multiply by 1 in a clever way by multiplying by the conjugate on the bottom and the top. If you FOIL it out, if you multiply across on the bottom, you end up with x minus 1. It's an important computation. Think that through. The square root of x times the square root of x create an x, and you'll have a minus root x and a positive root x for the middle terms. They cancel, just leaving minus 1 for the final two terms. Now I'm going to leave the numerator as it is. We could multiply it out or not. Doesn't really matter. The point being that at this point we can cancel the x minus 1 on top and bottom. And then we're just left with the limit of square root of x plus 1. Now that's great. This is a continuous function. We can just evaluate the limit at 1, and we get square root of 1 plus 1. That's 2. Okay, so we're going to see a different way of approaching this computation. And the key is that if we look at the original limit, if we just tried to evaluate naively, if we just plugged in the x value 1, what would happen? We'd end up with 1 minus 1 on top and square root of 1 minus 1 on the bottom. Well, that's our old friend. It's 0 and 0 on both the top and the bottom, so we get this indeterminate form. Remember, 0 over 0 doesn't mean anything. We've just computed that the numerator tends to 0 and the denominator tends to 0, and we don't know what that means in terms of the overall fraction. So L'Hopital's rule is a way of sometimes figuring out the answer when you have an indeterminate form like this. So what does L'Hopital's rule say in general? It says that if the limit of the top of some fraction and the limit of the bottom of some fraction, so I'm thinking of f and g as the numerator and denominator, if they both tend to 0 or they both tend to plus or minus infinity, so that the overall fraction f of x over g of x looks like 0 over 0 or infinity over infinity, both becoming unbounded. So you have to check that you're in this indeterminate form situation. If that's the case, then we can compute the limit of the entire fraction in the following way. L'Hopital's rule says that we can compute this limit by just taking the derivative of the top, the derivative of the bottom, and instead looking at their ratio, that fraction. Okay? So we can trade the top and bottom for their derivatives and then take the limit, as long as we check that we have these indeterminate forms. So how does that work in the example that we just discussed? So let's go back to the limit that we just computed. Remember that we found the limit to be 2. Well, we already saw that we have the indeterminate form. We've done that check, so let's just go ahead and apply L'Hopital's rule. If we apply L'Hopital's rule, that means that we just need to take the derivative of the top and the bottom. The derivative of x minus 1 is just 1, coefficient of x. How about the derivative of square root of x? Well, remember that's x to the 1/2, so we would have 1/2 times x to the minus 1/2 as the derivative of the denominator. Notice that subtracting 1 from 1/2 leaves that as the exponent. And now what is that? I claim that we can actually just evaluate this limit. That's because we can rewrite this term as 1 over 2 times the square root of x, right? X to the minus 1/2 means it's in the denominator of this subfraction, and the 1/2 means it's the square root. Okay, and now that's just the same thing, 1 over something again, right? 1 over 1 over, that just means take the reciprocal of that fraction in the denominator. This is the same thing as the limit of 2 root x. And now we can just evaluate. We get 2 times the square root of 1, and we end up getting 2. Once again, same answer as before. So L'Hopital's rule is a new way of computing fractions like this using the derivative. The key is that you have to check this indeterminate form. If you don't check that, if you just have some normal function, like 4x over 5x, something like that, or 4 over 5, and you don't check that you're in this indeterminate form, you could end up getting the wrong thing. So be careful about that.
Is a little confusing and a little unreal. That sense of unreality is because nearly every shot in this video is being played back at the wrong speed. We filmed this section at 30 frames a second, but it's being played back at 24, 80% of normal speed. So it just seems a little bit off. Plus, we're using rapid cuts with no continuity between them. Different clothes, different locations, different everything.
Let's look at another example of L'Hopital's rule. So the function here is 4 to the x minus 3 to the x minus 1 divided by x minus 1. That's a 4 there. Okay, now if we just naively evaluate, applying the limit sort of individually to the top and bottom, what happens? Well, something to the first power is just that number, right? 4 to the 1 is 4, 3 to the 1 is 3, so we get that on top, and then 1 minus 1 in the bottom. Okay, if you do the arithmetic here, they're both tending towards 0. So that means that we have the indeterminate form. L'Hopital's rule is applicable. That means we can compute this derivative, we can compute this limit by taking the derivative of the top and bottom individually. Not the derivative using the quotient rule, the derivative of each individually. What's the derivative of 4 to the x? Well, remember the derivatives of exponential functions. It's the natural log of the base times the exponential function itself. And similarly, the derivative of 3 to the x is natural log of 3 times 3 to the x. The derivative of minus 1, that's just 0, that's a constant. And similarly downstairs, the derivative is just 1. So that's much simpler. Now what happens if we take this limit? We no longer divide by 0. That's the magic of L'Hopital's rule. We were able to reduce from this linear term to a constant term in the denominator, and that means that we can just evaluate at 1. Okay. This limit will just be what we get by setting x equal to 1, and that's a well-defined number. There's no issues with division by 0. That's the limit.
We've also got some cutaways in extreme slow motion, because it looks spectacular, and because it lets me do a moody stare into the distance without having to hold it for so long that it becomes awkward. It also lets us fit in some product placement.
Here's a nifty application of L'Hopital's rule, and it's motivated by the following question. What is 0 to the 0th power? Have you ever thought about that before? It's a little bit confusing, right? Because if you think about 0 to the x, where x could be like 2 or 3, negative 5, some normal number, 0 to anything is equal to 0, right? But on the other hand, if we instead let the base be x, and we think about taking the 0th power of something, x to the 0, that just means multiplying x by itself 0 times, which is the multiplicative identity. It's just unity. It's just 1. Anything to the 0th power is 1. So we can think about the answer as either 0 or 1. Well, that's weird. In math, we're supposed to have a single answer, a single common value for 0 to the 0. So is it 0 or is it 1? What are we going to do? So in order to determine this, we're going to find the limit of x to the x. So I'm going to look at that expression like 0 to the 0. I'm going to think of it as x to the x, and then I'm going to let x approach 0. Now there's a bit of a technicality here. We can't take square roots of negative numbers. Things like that get a little bit funny, so I want to insist that we're never looking at a negative number. So let's approach 0 from the right, only with positive values of x. Okay, so we're going to find this limit, and then we'll think of that as a reasonable stand-in for 0 to the 0. Okay, but then how do we find that limit? how would we compute that? It's tough. There's a trick here. There's a trick. Here's a clever trick. Often in mathematics, things become easier if you first take the natural log. So here's what we're going to do. We're first going to take the natural log of x to the x. So I'm going to look at the natural log of x to the x, and then I'm going to use my exponent rules inside of the logarithm to write that as x times natural log of x. Right? Remember, in general, for any logarithm with any base b, if you look at a to some exponent c, that's always c times the log base b of a. That's a general rule for logarithms. That's always true. Okay, so here's the trick. We're going to instead compute this limit. Check it out. So let's look at the limit as x approaches 0 from the right of the natural log of x to the x. As we just saw, the natural log of x to the x, we can rewrite that as x times the natural log of x. Alright, and now you might say, well, this is a little bit funny. I know that natural log of 0 is not well defined. It's only defined on positive numbers. I guess this is going to 0. Like, I don't know, maybe it's 0. Okay, you can't really reason about it in such a vague way. You have to do something with mathematical precision. So here's another little clever trick. I'm going to rewrite x as 1 divided by 1 over x. Do you see how that works? If you have 1 over x in the denominator, then it gets to flip upstairs as its reciprocal, which is just x. So x is the same thing as 1 over x, and so these are the same function that we're taking the limit of. Well, if you look at what this expression does at 0, natural log of 0 is tending towards minus infinity. It's getting arbitrarily small. All right. Why is natural log tending towards minus infinity? Here, I'll show you. Remember the graph of the natural log function? The graph of the natural log function is sort of the flip along the line y equals x of e to the x because, well, it's the inverse function of e to the x. In particular, it goes through the point 1, 0. And this is the y-axis. This is where the x values are 0. So if we go along this graph, if we let x approach 0, then the output of the graph is going towards minus infinity. It's getting arbitrarily small. Okay, what about 1 over x? What does that approach as x approaches 0? Well, that approaches positive infinity because if you're dividing by a really small number, that's the same thing as multiplying by a really big number. So of course, this is not a number, this is just some indeterminate form, but the point is, having checked that we have this indeterminate form, we can use L'Hopital's rule to compute that limit. So let's do it. We now apply L'Hopital's rule. That means we take the derivative of natural log. Derivative of natural log is 1 over x. And we take the derivative of 1 over x. 1 over x is the same thing as x to the minus 1, so I can rewrite that this way as minus x to the minus 2. That's what I get from the power rule, taking the derivative of 1 over x. And now we're almost there. We just need to clean this up before we take the limit. Let's see here. We have an x to the minus 2 in the denominator. That's like a 1 over x squared. We can flip that up to the top. Okay, so then what happens? If we do that, I guess I'll write the minus 1 that's left over downstairs. So flipping it up, we get 1 over x times x squared in the numerator. So I flipped the x to the minus 2 upstairs as just x squared. Okay, so we end up with minus x. That's what that function is. And as you approach 0 from the right, minus x will go towards 0. So our intuition was correct. That limit is 0. We just needed to use L'Hopital's rule and this clever trick in this step in order to put it in a form where we could actually compute it. Okay, but careful. That wasn't quite what we wanted to do. Remember, we're trying to figure out what 0 to the 0 is, and the proposal is to compute this limit. That's not the limit that we just computed. It's the limit of the natural log of that we just computed. So in order to find the limit that we actually want, we're going to get rid of that natural logarithm that we introduced by now taking its inverse function. We're going to take the exponential of everything. All right. So check it out. Here's what I mean. The limit of x to the x, that's the same thing as taking e to the natural log of x to the x. So that's where we're using that the exponential function and the natural logarithm are inverse functions. They undo each other. If I take natural log of something and then e to that thing, well, this is exactly just whatever you have to raise e to get x to the x, and I just raised e to that. So it's the same thing as x to the x. That's true even before the limits. I'm just looking at the limit of these two equal functions on either side. Well, that's fantastic because we just computed the limit of the natural log function as x approaches 0, right? The exponential function is nice and continuous. We can just evaluate this limit by taking the limit of that inside piece. We just computed that it's approaching 0. So that means that this overall limit is e to the 0, right? This is going to 0, so we have e to the 0. What's e to the 0? E to the 0 is 1. Oh, cool. So this limit, in fact, is 1. And that's my argument. That's my sort of reason for saying that it's appropriate to think of 0 to the 0 as being equal to 1. That would be my answer. But I should warn you that, there are other opinions. There are some reasons to think of 0 to the 0 as 0. I'm not saying that this is firm. This is really an indeterminate form, but I prefer this answer, and it's justified by this limit calculation that we just made.
The trouble with filming everything in the wrong frame rate is that my voice won't sound right, so the vocal track for this was pre-recorded in a studio, and I'm lip-syncing it at the wrong speed. If my lips don't quite match up at some point, we'll just cut to another take or to a completely random slow-mo shot of an object being destroyed, and no one will care.